first we'll start the constant mapping. We'll define constant mapping. Constant mapping. So mapping FA to B. Mapping FA to B is called constant mapping. It's called constant mapping. If f of x equals to some element B for all x belongs to A. So this is your A set, this is your B, both are non-empty. So the mapping is called constant if the all elements of A goes to a single element of B. All elements of A, the image of all elements of A, basically a singleton set. Okay, and in that case, what is the range of F? The range of F is basically the singleton set B, where B belongs to capital B. Okay, so the range of F is basically a singleton set. A singleton set. Here we also write where B belongs to capital B. So this is the definition of constant mapping. As for example, so if we define the map F set of real number to real number by say fx equals to 2024 for all x belongs to R, then this map F R to R is a constant map. Is a constant mapping. Constant mapping. And if we asked here what should be the range of F, range of F will be 2024, that singleton set, and which is a subset of R. This is the note for this example. Now we'll give another definition of another kind of mapping. This is called the identity mapping. So next definition about identity mapping. Identity map. What is the definition of identity mapping? A mapping. Here the domain and codomain both remain same, FA to A, while A is basically a non-empty set. So mapping FA to A is called identity mapping. Is called identity mapping. If f of x equals to x for all x belongs to A. So this is your set A again. So this is x1, x2, x3. So x1 goes to x1, x2 goes to x2, and x3 goes to x3. So that means the image of an element, again the same element. Okay. So the identity mapping at the note, the identity mapping is denoted by, identity map is denoted by I suffix A. So that means I suffix A is a map from A to A, while x goes to x. Okay. So now we'll give one example. So let f R to R. So this is our example. We define by fx equals to x for all x belongs to R. Okay, and this is then F is an identity mapping. And we denote it I suffix r. Okay, so this is the example. You can think about different examples. So you can clearly it is conclude that. So one important recall or remark: the identity mapping is a biject is an example of a bijective mapping because it is injective as well as surjective. So you can check it. Identity mapping is a bijective mapping. Whereas the constant mapping, you will recall here, the constant map f from A to B, where the cardinality of the set B is greater than equals to 2, is neither injective and nor surjective. So this is not a bijective mapping, the constant map. Now we come to another important recall: restriction mapping. Now next we'll talk about restriction mapping. So let A and B are both non-empty set, A non-empty set, B non-empty set, and S is a non-empty subset of A. This is also non-empty. Okay, so S is also non-empty subset of A. And let F is a mapping, F A to B, B a mapping, and S is non-empty subset of A. S is non-empty subset of A. Then, so this is your A and this is your set B, and F is a mapping from A to B. Now we have set a non-empty subset S. We are trying to restrict the map F on the set S. How? So then the map, so I have taken the map G here. G is to be defined by G of x equals to fx for all x belongs to S. That map is called the restriction of F, restriction map of F on the set S, and it is denoted by F restriction on S from S. Okay, so this is basically called the restriction map. So now the restriction map, if we take one good example about the restriction map. So example, let we define a map if R to R be defined by fx equals to, this is one of the famous map, 1 and 0 for all 1 when x is a rational number, and 0 when x is basically irrational number, set of all irrational numbers. In that case, the restriction map, then we define the restriction map, then the restriction map, if I am restricting on the set Q to R, this map is given by if restrict over Q of X, this is equals to 1 for all X belongs to Q. So this is the example of a restriction map. Again, if we restrict on the set of irrational number, in that case the map will be 0. Now we come to another important definition of this is basically composition of mapping. Composition of mapping. And this definition is very important. Composition of mapping. See here you have taken a map FA2. What is the definition? The definition is let F A to B and Z is a mapping from C to D, B to mappings such that FA is subset of C. Okay, so that means that is range of F subset of domain of G. Then the composition of map. So this is your A, B, and F is a function from A to B, and this is just you can consider as the range. This is considered the range of F, and this is basically subset of dome of G. So you just consider this is the C and to D. So this map G. So here you just see range of F subset of dome G. Then we can define the composition. The composition will be G composed F, and that is basically A to C. Then the map, we just consider the map. Then the map G composed F from A to C is defined by G composed Fx equals to G of Fx for all x belongs to A is called composition of mapping. Composition of map F and G. This is exactly the definition of the composition of mapping. Now you have given two mapping and you need to find out the composition. Now the question is how to find out the composition of these two mapping. So I'll give the example. Say you have given example. Let F R to R and G is also mapped from R to R. Here you will see the range of F must be subset of dome G. So we can define the G composed F. We defined by what is Fx? Fx equals to x plus 1 for all x belongs to R, and Gx equals to 3x for all x belongs to R. Then find then find F composed G and G composed F. And next, verify if composed G equals to not equals to G composed F. That we need to verify. So how to solve this kind of problem? So here f is a function from R to R. F is a function from R to R. This function is f. And G is also function from R to R. So we need to define G composed f here. So fx, here x goes to x plus 1, and here gx, that x goes to 3x. We need to compose, since f is a function from R to R and G is also function from R to R, and also range of f, this is subset of dome of G. Okay, so what we can write, so G composed f, this is also R to R, is defined. Now the question is, what should be the G composed f? So now we need to calculate G composed f. This is basically also R to R, is given by, is defined as G composed f of x, that will be G of fx. The question is, what is fx? This is basically x plus 1. That is G of x, this is 3x. So it will be 3x plus 1. So what we have got here, therefore G composed f R to R is G composed f of x, that will be 3x plus 3 for all x belongs to R. Again, what we will calculate? So this is again G. This is a function from R to R. F is also function from R to R. So obviously we can define here f composed G. This will be R to R. And we just check here the domain of f. This is a superset of range of G. Okay, so domain of f is basically R. So that means we can define, since again G is a function from R to R, f is also function from R to R, and also if we calculate range of G, that is subset of dome of f, this is also R. So what we can say, f composed G R to R, this is defined. And what should be f composed G of x? That will be f of gx. So that means f of 3x. And f of x equals to x plus 1. So that will be 3x plus 1. So therefore, f composed G R to R is f composed G of x, that will be 3x plus 1 for all x belongs to R. So this is, you can consider 1, that you can consider 2. So here 3x plus 3, here 3x plus 1. So we can easily say, therefore, from 1 and 2, we say that f composed G not equals to G composed f. So as for example, if we take f composed G of 1, that will be 3 into 1 plus 1, that means 4. And G composed f of 1, that will be 3 into 1 plus 3, that will be 6. So that means F composed G of 1 not equals to G composed F of 1. Okay. Now the question is when two map will be equal. That you need to understand here. Recall the when the map F A to B, say F is a mapping from A to B and G is a mapping from A to C, and G is a mapping from A to C are equal. Okay. Now two map F and G are equal if it satisfies the following condition. So our answer is if Roman 1 domain of F equals to domain of G, and Roman 2 image of F equals to image of G for all element in A. So Fx equals to Gx. That implies then we conclude that F equals to G. Okay. So what I conclude, to map will be equal if and only if two condition holds. Fx equals to Gx for all x belongs to A, and 2 domain of F equals to domain of G. Okay. So if we see note, if we see domain of F not equals to domain of G, from that we can conclude F not equals to G. And also another way, if we see there exists an element X belongs to A such that the image are not equal, in that case we conclude the map is also not equal. So in these two ways we can conclude the map is basically not equal. So here what we have seen, that means if composition of mapping is not commutative. So our comment is, our conclusion from the previous example, from this example or questions, the composite GF composed G not equals to G composed F. So that means our conclusion is composition of mapping is not commutative. So that means, that is, if we take three mapping FGH, so F composed G not equals to G composed F. So here the example is, if we take F R to R, the X goes to X plus 1, and G is also mapped from R to R, where X goes to 3X. Okay, if this, then our G composed F R to R, this map is X goes to 3X plus 3, and F composed G is R to R, this map is X goes to 3X plus 1. So what our observation? Our observation is here, the F composed G not equals to G composed F. But there is another important recall. The composition of mapping is associative. Recall, the composition of mapping is associative. So that means what I am saying, if F, G, H are three maps and the composition is defined, and all composition are defined, then we can say F composed G composed H equals to F composed G composed H. So this is true. Composition of map is associative. Now you need to provide one example where the composition may be commutative. Okay, so we'll provide this example. So question is, or this is question 2 in that case. Let F is a mapping from R to R and be defined by fx equals to x plus 1 for all x belongs to R, and G is also mapping from R to R. Be defined by g of x equals to x plus 5 for all x belongs to R. Then first thing, find F compose G and G compose F, and second thing, just verify F compose G equals to G compose F in that case. So here we move to the simple solution. So here we just see dome of F, it is superset of range of G. So that implies F composed G R to R is defined, and what is F composed G of x? That will be F of Gx. What is Gx here? F of x plus 5. What is Fx? X plus 5 plus 1. So this will be x plus 6. Okay. So for all x belongs to R. And since again a range of F subset of domain of G, this is basically R, and that implies G composed F R to R is well defined. And the question is, what is G composed F of x? This is G of fx. So that means G of x plus 1, and that will be x plus 1 plus 5, again x plus 6 for all x belongs to R. So therefore what we observed here, F compose G equals to G compose F. This is our observation. Now we come to some important questions, and you need to find out the F compose G and G compose F. And the question is, this question is very, very important for graduation level. So what is the question? Let F is a function from Z to Q and G is a function from Q to Q be defined by f of x equals to x by 2 for all x belongs to Z, and g of x equals to x square where x belongs to Q. Then compute F compose G and G compose F. So we have solution. So Z to Q, here your map is F, and Q to Q, your map is G. Now we need to define here G compose F, that will be Z to Q. So since our range of F, that is subset of Q, and this is basically domain of G. So that means G composed U, Z to Q is defined. So if diff is defined, therefore, and hence, what should be the G composed F of x? That will be G of fx. What is G of fx? Fx will be x goes to x by 2. So that will be x. What is g? That will be x square. So that means x by 2. That whole square. It will be x square by 4. So that means G composted J to Q is defined by G composed f of x, that will be x square by 4 for all x belongs to Z. Now we'll calculate f composed G. So G is basically Q to Q. This is basically, then F is basically J to Q. F is Z to Q. Okay. So is it possible to compute F compose G? Is it possible? So here, this is our observation. F compose G is not well defined. Is not defined. Is not defined. Now the question is why? Why it is not defined? Because as range of G, this is basically all the Q plus union 0, and this is not a subset of Z. Z is domain of F. Okay, so because the x goes to x square, so obviously that does not belongs to Z always. So as for example, if we take 1/3 and that square is 1 by 9, so this is that not belongs to Z. Okay, since 1/3 1 by 9 belongs to range of G, but 1 by 9 does not belongs to Z. So that implies F compose G is not defined. Okay. Now the question is, if we take two injective mapping, the composition of two injective mapping is injective or not. Okay. If we take, next we come to some important theory here. Theorem 1, say if F is a map from A to B and G is a map from B to C. We both injective mapping. Then the composition map, G composed, this will be A to C is injective. So how to prove this kind of problems? So you have given a theorem. If this is basically A to B and G, this is basically B to C, and we have to prove G composed. So this F is injective, this G is also injective, and we have to prove G composed F A to C. That means composition of two injective mapping is injective. So how to prove? We'll prove this theorem if we take two element in A and if we take the image are same, then the elements are same, then in that way you can prove the injectiveness. Okay, so you just take two distinct elements here, x and y, or two elements x and y. So let x comma y, let x comma y belongs to A be such that G composed F of x equals to G composed f of y. Okay, since G composed f is well defined, what will show then? What will show G composed f of x equals to G composed f of y? That must implies x equals to y. That we need to show. The question is how we have to show. Here we have to apply the definition. We can write G composed f, G of fx, that will be G of fy. Now since G is injective, since G B to C, this is injective map. This is injective. So here G of alpha equals to G of beta. That must implies alpha equals to beta. So that means this must implies fx equals to f of y. And that implies x equals to y since f is injective. A to B is injective. So fx equals to fy, that implies x equals to y. So that means what we achieved here. So therefore G composed f of x, this is equals to G composed f of y for all xy belongs to A. That implies x equals to y for all xy belongs to, as xy belongs to is arbitrary. So that means G composed f A to C, this is injective mapping. Injective. Now the question is the converse is true. Now the question is the converse true? For the previous problem, that previous theorem, the composition of two injective mapping is injective. If the composition is injective, then F and G will be individually injective or not? Okay? No, that may not be true. So the answer is no in general. In general, the converse is not true. So what is talking? So that means if our comment or recall is here, if G composed F is injective, then F is injective, while G need not be. It may not be injective for the case G, but F is always injective. That we can establish. So, in order to verify this recall, I'll give you the example where G composed F and F will be injective, but G is not injective. So, as for example here, let F is a function from R to R be defined by fx equals to exponential x for all x belongs to R. So this is like this kind of graph. Fx equals to exponential x where we have take and g is a function from R to R be defined by g of x. This is basically x square for all x belongs to R. So gx basically x square. So here you will see this is not injective, because if we take 1 and minus 1, you will see g of 1 equals to g of minus 1, but 1 not equals to minus 1, and from that case you can verify gr2r is not injective. So then what will be G composed F? The composition is defined. Why the composition is defined? G of Fx, because since uh, range of F, that will be basically R plus is a subset of domain of G. This is basically R. So G of Fx. So G, what is Fx? Exponential x. So that means e to the power 2x for all x belongs to R. So G composed F is e to the power 2x. And this is also an injective mapping. Again, the graph is like this, e to the power 2x. This is G composed F. So what is our G composed F here? So here what we have seen, what we have seen, so therefore G composed F is injective. You can check easily, since G composed F x equals to G composed F y, that implies x equals to y for all xy belongs to real numbers. So it is injective. But you will see here, G is injective, but F is injective, but G is not injective. So our comment is a G composed F and F both are injective, but G is not injective. Why G is not injective? So this is our explanation. So what we have seen, the composition of two injective mapping is injective, but the converse is not true. That means G composed F may be injective. In that case, we will always observe F is injective, but sometimes G need not be injective. So this is the counter example for this kind of recurrence. Okay. So thank you.